Hello, my name is Qianjun Hang. I'm a postdoc at the University College London. Today, I will talk about my work on probing galaxy group correlations in redshift space with the HALO streaming model using the GAMA data. This is a work done in collaboration with John, Shadab, Chai, and Katrina, mainly at the University of Edinburgh. And if you want to know more about this work, then you are more than welcome to check out the paper on arXiv. So let's start with a short introduction to the GAMA survey. This is a spectroscopic survey that covers 5 distinct fields on the sky. The 3 main fields are G09, G12, and G15 near the equator, and each one of them covers an area of 60 square degrees. There is a R-band magnitude limit for the survey of 19.8. So most objects are found near redshift 0.2 or so. What's really amazing about this survey is that it has a very high completeness in terms of the galaxy spectra measured. This means that we can construct very robust galaxy group catalogs using algorithms such as friends of friends. In this study, we will use groups with 2 or more members, and we select our samples between redshift 0.1 and 0.3. On the right-hand side plot, you can see where these groups are distributed, especially in 3 main gamma fields. With a spectroscopic survey like GAMA, one interesting study you can do is to measure the Redshift-Space Distortion effects. This arises from the fact that due to the expansion of the universe, the galaxies have the Hubble velocity. These velocity then gives rise to the redshift of the galaxies. And from there, we can infer how far a galaxy is from us. However, on top of that, galaxies also have peculiar velocities. The radial component of these peculiar velocities also contribute to their redshift. And so when we are calculating the galaxy distance from their redshift, it's actually distorted from where the galaxy truly is. These peculiar velocities can be understood on 2 scales. On large scales, they arise from the fact that galaxies infall into the gravitational potential of the large dark matter halos. This can be roughly illustrated here, where if you have a circular distribution of galaxies around a halo, then along the line of sight, what you see is that they become slightly squashed. This effect is first characterized by Nick Kaiser, and so it's often referred to as the Kaiser squashing. On smaller scales, on the other hand, galaxies have random velocities due to the virial motion inside a dark matter halo. This means that now if you have a circular distribution of galaxies, then they will appear elongated along the line of sight. And this is often referred to as the fingers of God. Both of these effects can be seen on the galaxy 2-point correlation function when you measure it along and perpendicular to the line of sight, as shown in this middle sketch here. The dashed line roughly separates the large and small scale effects that you may be seeing. Now, the RSD effect is sensitive to a very important cosmological parameter, the growth rate parameter of the underlying matter field. This is because these velocities directly correspond to the gravitational potential generated by the matter fluctuation. And it is for this reason, RSD is often regarded as a test of the theory of gravity. Now, with the high completeness of the GAMA survey, one can go a step further by measuring the RSD using different tracers. This is essentially splitting the density fields into different values. One tracer we use is the galaxy groups. These groups are generally thought of as sits at the peaks of the density fields. We further split our group sample into 3 stellar mass bands, and we call them the low mass, medium mass, and the high mass bands. Another tracer we use are the galaxies. And for these, we separate them into the blue cloud and the red sequence in the apparent G-I color, as illustrated on the right-hand side plot. The separation of the population is meaningful because the bluer galaxies are generally younger and star-forming, and are likely to be found as the satellite galaxies around a dark matter halo. Whereas when you look at the redder galaxies, they are more likely to be old and quenched and associated with more massive halos. So overall, we have 6 different subsamples to do the cross correlation. Red and blue galaxies cross-correlated with the low mass, medium mass, and high mass groups. The measurements from gamma are highlighted in these red boxes. And on the top row, we also show the autocorrelation of the galaxies. You can see immediately that when you compare the red and blue subsamples, the red samples have a much higher signal, and that means much stronger clustering compared to the blue. Not only that, the red samples also have a much enhanced finger of God effect. You see that this effect is most obvious in the galaxy autocorrelations, but when you separate them by different group masses, this difference is reduced. Another interesting observation is that when you look at from low mass groups to higher mass groups, you see that the nonlinearities in the middle grows significantly. So a natural question arises then, given all these different measurements, could we recover a single growth rate from them? Or would this be tracer dependent, for example? To answer this question, one, we need a good model for the RSD. Well, the simplest model is the quasilinear dispersion model. This is essentially a Kaiser linear model, but with the linear power spectrum replaced by the nonlinear one. This replacement allows you to go slightly into the nonlinear region. In this famous Kaiser equation, the mu squared terms gives you the squashing effect on the large scales, and how much squashing there is controlled by the beta parameter, which in turn depends on the growth rate f and the bias of your tracers. And to include the fingers of God effect, people often multiply the redshift space power spectrum by an anisotropic velocity profile as a damping term. And this often takes the form of a Lorentzian function. Here, the free parameter is sigma 1, 2, the velocity dispersion, which tells you how much smearing you have along the line of sight. So the quasi-linear model describes the large scale features well, but as you go down to scales below 10 to 20 megaparsec, it begins to fail. So in order to go to smaller scales, one idea arises from the halo model is that you can separate your 1 halo and 2 halo terms. This makes sense because on very large scales where linear theory would apply, you're essentially correlating objects from 2 different halos. Whereas on smaller scales, you are correlating objects within the halo. And that could be much more complicated compared to your linear theory. In this work, we adopt a Gaussian streaming model for the 2-halo term because it allows a slightly better extension into the quasilinear regime. And for the 1-halo term, in real space, you would think that this is straightforward because this would just be an FW profile. However, in Redshift space, due to this large random virial velocity, it is actually non-trivial to write down any semi-analytic here. It should also be apparent that the two terms would require very different velocity dispersions because these velocities arises from different origins. So in this case, we take an empirical approach for the 1-halo term. What we do is we extract the 1-halo term from the mock catalog and use it as a template when we fit it to data. The procedure is essentially illustrated on this 3 panels here. And on the rightmost panel, I'm showing you the extracted 1-halo template from one of our 6 subsamples. One striking feature you see is that at RP equals 0, you have this very large velocity dispersion that giving you the fingers of God effect. But as you go to slightly larger RP, the contour becomes almost circular. This tells you that the velocity dispersion for the 1-halo term must be strongly scale dependent. And it drops to almost 0 as you go to the edge of the 1-halo term. Now we do this for each one of the 6 subsamples, and we also include 2 nuisance parameters, alpha and eta, which suggest the overall amplitude of the template or stretching it or squashing it along the line of sight. So we validate our empirical model, which we call the halo streaming model, on a set of mock catalogs. What we do is we apply it to each individual mock sample, and then we calculate the averaged best fit growth rate from this. We also do this at a few different minimum scales included and compare that with the quasilinear dispersion model. What you see is that for the QD model, it fails to recover an unbiased growth rate below a scale of 10 megaparsec or so, whereas the HS model gives you consistent value even down to a scale of 2 megaparsec. Now we can apply these models to the gamma measurements, and these are shown on this plot here. The growth rate measurements are shown on the top row, and what you see is that for each one of the subsamples, the measured growth rate is consistent. So this is reassuring. However, when you compare them with the Planck fiducial value, which is shown by the black line on top, you see that they are lower by about 2 sigma level. Looking at other parameters such as the group or galaxy biases or the velocity dispersions, we find that these are in qualitative agreement with other gamma studies. Finally, in all these results shown here, we have marginalized over the nuisance parameters for the 1-halo term. Now, coming back to a slightly lower F sigma 8 measurements from gamma, this is perhaps not too surprising because in other gamma measurements, which are consistent with ours, it is also lower than Planck, but with much less statistical significance. This could actually be due to the fact that gamma is just a special field it has such a small coverage on the sky, so the cosmic variance must be very large in this case. We already know that, for example, there is a substantial dip in the number density in gamma fields at redshift about 0.24. So this could be, for example, a local large-scale structure overlapped with all three of our gamma fields. And this demonstrates the significance of cosmic variance could do on your small survey fields. It would also be interesting to consider this from a slightly different angle, where recently from weak lensing studies, it is suggested that the sigma 8 parameter could be lower compared to the Planck value by about 10%. Now, if that is true, then our result would definitely be closer to this revised fiducial value of F, or F sigma 8, but there is still about 1 sigma difference. So whether this slightly lower measurement is due to a statistical fluctuation or cosmic variance, or it provides a different perspective to the sigma 8 tension, I think it will be answered very soon in the future when we have data from the DESI BGS or the WAVE survey. In these surveys, the area covered will be almost full sky. And therefore, the cosmic variance will definitely be beat down, and we will have a much tighter constraints on the growth rate parameter. So I'm very looking forward to how these surveys will tell us more about the growth history of the universe. So I'll leave my summary here. We measured the group galaxy cross correlation in 6 subsets from gamma. We developed an empirical model called the halo streaming model to disentangle the strong finger of God and linearize the effects. Our nominal growth rate is consistent across all subsets. However, it is lower than Planck by about 2 sigma. The future surveys, future data sets such as DESI, BGS, and WAVES will definitely provide tighter constraints on the growth rate. And maybe this will be able to shed light on the sigma 8 tension from a different angle. So thank you for your attention.